In this video, we will bring together everything we've learned about electrophilic and nucleophilic aromatic substitution reactions to practice synthesis of substituted arenes. The term arene generally means aromatic molecule, and there's a wide variety of aromatic molecules. Our discussion has largely been limited to benzene and substituted benzene or benzene derivatives. These are examples of arenes. And then if we're referring to some benzene substituent or benzene group or arene group, this is sometimes called aryl. Okay, it's a substituent on X from this perspective. But benzene is not the only arene. We will very briefly discuss some other arenes. So just keep in mind that arene is a more general term that means aromatic molecule, and it includes these nitrogen heterocycles. But the bulk of our discussion in this lesson will be limited to benzenes and substituted benzenes. One of our learning goals today are to predict the products of common reactions of aromatic molecules. Now, a few of these common reactions are electrophilic aromatic substitution or nucleophilic aromatic substitution reactions that we haven't learned yet. But there are also some fun, we can call them grab bag reactions, just common reactions that don't fall in either of those categories, but that we need to learn. So we will be learning those and adding to our reaction charts. We will apply electrophilic aromatic substitution and nucleophilic aromatic substitution mechanisms in complex settings, probably these new reactions we're going to learn, and then propose syntheses of di, tri, and tetra substituted benzene rings using directing groups and blocking groups, ooh, sounds fun, as necessary. I have decided to begin today a little bit differently. We'll begin today's lesson by writing out our reaction chart, so introducing the new reactions that will be learned. First up is oxidation of the benzylic position of an alkyl benzene to make benzoic acid. When any alkyl benzene that has at least one benzylic hydrogen, recalling that the benzylic position is adjacent to the benzene ring. When any alkyl benzene containing at least one benzylic hydrogen is treated with aqueous potassium permanganate under basic conditions, the entire side chain is chewed off, oxidized off to generate a benzoic acid. You can see how the benzylic carbon is oxidized from an alkane to a carboxylic acid. Wow, from 0 bonds between carbon and oxygen to 3 bonds between carbon and oxygen. Certainly an oxidation reaction. And you can note if there are multiple R groups with benzylic CHs, then all of those R groups will be oxidized to form carboxylic acids. Next up, reduction of nitrobenzenes to anilines. When nitrobenzene, or some substituted nitrobenzene, is treated with a reducing agent, such as iron metal in the presence of hydrochloric acid, and zinc metal works as well, the nitro group of the nitrobenzene is reduced to an amino group. And aminobenzene has a name, its common name is aniline. So nitrobenzenes can be reduced to anilines. This works for the parent compound or for substituted nitrobenzene. Next up, diazotization of an aniline. If aniline, either the parent compound or imagine that we begin with some substituted nitrobenzene, we'll have a substituted aniline. If that compound is treated with sodium nitrate in the presence of hydrochloric acid, a really interesting product is formed, and it's called an aryl diazonium salt. Aryl diazonium salt. See that ionic bond there, right? Okay, so this represents the diazotization of an aniline. Now, who in the world would ever want to make one of these compounds? That looks totally random. Great question. Well, a lot of people, because there are many reactions that these diazonium salts can undergo to make many different types of substituted arenes, substituted benzenes. Let's take a look at some of those reactions now in summary, and we'll discuss them in greater detail in just a bit. If you have been wondering how one can make aryl fluorides, how one could make fluorobenzene, you're in good luck today because we're going to learn how. Fluorobenzene can be generated from this aryl diazonium salt by treatment with tetrafluoroboric acid. Okay, and this will work for the parent compound or, a substituted aryl diazonium salt. We've already learned one way to make aryl chlorides and a similar method by which to make aryl bromides. However, aryl diazonium salts can also be converted into aryl chlorides and aryl bromides, and oftentimes this is the desired method for reasons that we will discuss shortly. Well, aryl bromide is just a more general term for bromobenzenes, but it means the same thing. When an aryl diazonium salt is treated with copper 1 chloride, chlorobenzene is formed. When aryl diazonium salt is treated with copper 1 bromide, bromobenzene is formed. As we will discuss, these two reactions proceed by radical mechanisms, meaning one electron chemistry. And in fact, copper 1 cyanide will react with aryl diazonium salts to generate aryl nitriles, which is exciting because we have not previously discussed a method by which to make aryl nitriles. I believe you're beginning to see how versatile of an intermediate diazonium salts are. There are methods to generate fluorobenzenes, aryl fluorides, aryl chlorides, and aryl bromides. What comes next? Yes, aryl iodides. Finally, we have not discussed a method for synthesizing iodobenzene yet, and the aryl diazonium salt will provide us with that synthetic route. So aryl iodides or iodobenzenes, where this plural benzenes is just really referring to if there's a substituent on the ring, then it's an arene or a substituted benzene. This reaction is a bit different than the others, and it requires treatment with potassium iodide. And we'll discuss the mechanism for that reaction later in the video. These aryl diazonium salts can also be used to make phenols. This is an exciting reaction because we have only really learned one way to make phenols, and that was by nucleophilic aromatic substitution, which has a pretty limited scope of substrates because an orthopara withdrawing group was required in order for that reaction to occur. This reaction of an aryl diazonium salt with water to generate a phenol is much more general and can be used much more widely in the synthesis of aromatic molecules. You're beginning to see the wide variety of reactions of these aryl diazonium salts. The reactions with water and potassium iodide are actually thought to proceed via SN1 chemistry, whereas these reactions with copper chloride, copper bromide, copper cyanide, as I mentioned, they're thought to go by single electron chemistry radical mechanisms, and we will not discuss these mechanisms in too much detail. The N2 group on the aryl diazonium salt can even be replaced with a hydrogen. What? Why would you ever want to do that? Well, there are some reasons. You remember this blocking group? So sometimes we put a group on a benzene ring to serve a purpose, but then need to remove it. And we'll find that this is a good reaction to remove a blocking group. However, overall, it substitutes the N2 for H by treatment with hypophosphorus acid. And finally, an azo coupling can be conducted by treating the aryl diazonium salt with an electron-rich arene to generate an azo dye. With that introduction to common reactions of aromatic molecules that we have not yet discussed in our electrophilic aromatic and nucleophilic aromatic substitution reaction lessons, we are ready to both discuss these new reactions a little bit more deeply and then start integrating them into our existing knowledge to propose more complex syntheses of di, tri, and tetra substituted benzenes. We will do this in a series of videos. So when you're ready, move on to the next one.